Hello everyone. In this session we will see Zbus derivation for branches. In the last session we have seen Zbus building algorithm formation. There we have observed four types of modifications we have done for the network. Those are type 1, type 2, type 3 and type 4. In type 1, type 2 modification, the added element we will call it as a branches, and type 3, type 4 we will call the added elements as a links. Out of 4 derivations, in this session I am going to teach you the first 2 derivations. If you understand these first 2 derivations and you can understand the derivation for the links effortless. Let us see the derivation. Let us consider the partial network. Okay, so by now you may know the meaning of partial network. So we are not considering all the nodes existing in the network. So we are considering only the partial set of nodes. So let us see what are the nodes that we are considering here. Node 1, 2 and so on. Ith node, jth node, nth node, and we will consider the reference node. So what are these ith node, jth node and the nth node? Nth node maybe your network is having some set of 100 nodes or 150 nodes. In that few nodes we have picked, that is 1, 2 and so on, ith node, jth node. So in this network all these nodes represent the nodes which are exist in the network. So we will call all these nodes as a old nodes. Now this reference node will be called as a reference node only. If you recall the type 1 and the type 2 modifications, type 1 modification I have told you, whenever you add an element between a new bus to the reference bus, okay, new bus to the reference bus, that fall into the category of the type 1 modifications. So in that case you need to form the what is the Zbus matrix. So that is what we are going to do now, and similarly we are going to derive the expression for the type 2 modification. So type 2 modification is whenever we add an element between new bus to the old bus. Now for this derivation we need 3 types of buses. One is the new bus, another one is reference bus, next one is old bus. So now first let us try to understand where are these buses. So what are the notations that we are giving for these buses. So in this network you can see already 2 types of the nodes. One is reference node, already we have, and another one is old nodes. All these nodes are called as a old nodes. Any node we can consider it as a old node. So since we are doing the derivation, I have generalized the old nodes with the letters I and J. Okay, so we are going to use this I and J as old nodes for our derivation. Now if you come to the concept, any matrix will have 2 types of elements. So one is the diagonal elements, another one is the off diagonal elements. So for this derivation also we are going to find out what is the formula to find out the diagonal quantities and what is the formula to find out the off diagonal quantities. Okay, so by deriving these 2 expressions, now we are going to write the equations for the type 1 and the type 2 modifications. And this is the basic idea that what we are going to do in this derivation. So now let us start with our derivation. You know, in the short circuit studies you might have studied that the short circuit analysis will be done by using the current injection method. Okay, so the same method we are going to follow in this Zbus derivation also. So reference node always it's connected to the ground line, so which will be having the 0 potential. Now let us consider the current with respect to the each branch. So I1 bar with respect to second node I2, with respect to ith node it is II, and Ij and so on In. Whenever the nodes exist in the network, there will be some potential difference between the nodes. So let us mark the potential difference of each node with respect to the reference node. First node to reference node, let us consider the voltage V1, and the second node to the reference V2 and so on. So we will have Vi, Vj and with respect to nth node, we have voltage Vn bar. So in the primitive network concept itself, we have seen the relation between the V bus and I bus is V is equal to Z into I. So by using this basic expression, now we are going to derive the equation for the Z bus. Let us see. If you come to the what is the matrix size of this V bus is, it is the column matrix of dimension n by 1, and I bus is also a column vector of the dimension n by 1, and Z bus is the n by n matrix. Now let us see the matrix representation to these parameters. So V bus matrix, so voltages of all the nodes V1, V2 and so on, ith node voltage, jth node voltage and so on, nth node. Similarly, let us mark the I matrix, I1 to I2, the corresponding currents II, Ij and In. So now the Z bus matrix, so between V1 to I1 it is Z11, V1 to I2 Z12 and so on. V1 to II is Z1i, Z1j and so on, Z1n. Similarly, you can fill the respective Z matrix values. Zi is the impedance exists between the ith node to ith node. So you can see here we have the diagonal elements Z11 to Znn, and the rest all are the off diagonal elements. So means we are going to derive two equations, one for the diagonal quantities and another one for the off diagonal quantities. Let us mark the dimensions here too. V matrix is a n by 1 vector and Z is n cross n and the current is n by 1. So this Z bus matrix is called the Z bus of the partial network or the Z bus old matrix. Okay, so wherever we are representing the Z bus old matrix, then you can represent this complete matrix as a Z bus old. Type 1 modification. As I said, the type 1 modification is when an element is connected between a new bus to the reference bus. So let us consider the partial network. So now we have partial network 1 to n nodes already exist in the network. So now we are connecting an external element between a new bus to the reference bus. So now we are not seeing anywhere the new bus. New bus in the sense which is not existing in the current network, we are going to bring newly to the existing network. Means if you are laid down some extra transmission lines, so then how we are connecting those nodes to the existing bus? Okay, from a new location to the existing network. So now element is nothing but a transmission line. Node is like which point we are taking the transmission line. So now let us consider kth node as a new node which is not existing in the network. Now we are bringing this node to the existing network. So we are connecting a transmission line, or you can say an element between the kth node and the reference node. What changes that are happening to the network? How are we going to solve this? Usually we do by using the concept current injection method. The same method we are going to follow here also. Let us add an element between the kth node to the 0, that is the new bus to the reference bus, which is having a branch impedance of Z suffix B. Okay, so element also will be called as a branch. Why we are calling it as a branch? We have added an element between the new node to the reference. Now how to represent the Z bus new? Okay, after adding the kth node, that is the new node. So we have brought a new node to our existing network. Now how are we going to incorporate this kth node in the already existing Zbus old. Okay, if you add this kth node into this Zbus, you will get the Zbus new matrix. Let us see that. So Zbus new equal to, so we have already Zbus old matrix which is formed between the 1 to n number of nodes. That matrix is called the Zbus old because it is already exist in the network. So now we have brought the another node which is the kth node. So that we have to add. So what is this Zbus old matrix which we have represented in the previous step? Okay, so that whatever elements are there previously, you can take it as it is. You can copy as it is to your next step. Then we have to add the kth node. So let us add the kth node. There will be always some impedance exist between the existing nodes and the new nodes. So that is what now our interest is. Okay, we are going to find out those element values. So now let us mark those values. That is first row to kth element we are forming. So that is why it is Z1k. Okay, so the first element always represents the rows position. Second place always represents the columns position. Okay, that is how we do represent the elements inside the matrices. So now Z2k and so on, Zik, Zjk and Znk. Similarly, let us mark the row elements. You have a kth row and you have 1 to n columns. So let us add the elements Zk1, Zk2 and so on, Zki, Zkj and Zkn. And the diagonal quantity is formed between kth element to kth element, which is a Zkk. We know one point, Z1k will be equal to Zk1. So Z2k will be equal to Zk2, Zik will be equal to Zki and so on. So now you need to calculate one equation to find out the off diagonal elements and one equation to find out the diagonal elements. Two equations we are going to find out for type 1 modification. With this already we have a old matrix of the dimension n. Now you have brought one node extra to the existing network. So the total new bus matrix dimension will increase by size 1. So this becomes n plus 1 by n plus 1 matrix. Okay, that is why you will call an added element is a branch. Okay, whenever an element is going to increase the size of the matrix by 1, so that element always we will call it as a branch. Links will not increase the size of the matrix. Okay, but there will be some effect of the link on the existing elements, but it is not going to change the dimension of the matrix. Yes, now you need to find out the off diagonal elements and the diagonal elements of this newly added node. Let us see that. Diagonal element Zkk. So we know Z is equal to V by I. Whenever you say the K and K element, the first position will go to the first letter will go to the numerator and the second subscript will go to the denominator. Okay, that is how I have represented Zkk equal to Vk by Ik. From this you can write voltage with respect to the kth node is equal to the current flowing through the kth node injected into the kth node and the Zkk. Kth node just now we have brought newly to the existing network. So then how to get the kth node means, here we are going to use the method current injection method. What will be the magnitude of the injected current is, we just inject the 1 per unit to the kth bus and we will assume all other buses are open circuited and we will compute the voltage with respect to the kth node. So I have taken the same network which I have represented. That's an element is added between the kth to reference node. Now we are going to inject the current at the kth node of the magnitude 1 per unit and there will be some voltage. The voltage appear across the kth node to the reference node will be V suffix k. So now you can see the V suffix k is equal to I suffix k into ZB. Let us consider this as equation number 1b, and so we have already considered the v suffix equal to ik into zkk as equation 1a. Now from equation 1a we know v suffix k. Now if you compare, because both the equations represents the same, that is the voltage across the kth node. So according to this you can say here ik and ik is same, and you can compare zv equal to zkk. So therefore the diagonal quantity zkk is that's just the branch impedance. Next, let us see the calculation for the off diagonal element. Zkm equal to Zmk, as I said, where m represents the number of nodes existing in a partial network. And we know Zkm can be represented as v suffix k by I suffix m. Let m is equal to j. Okay, so m node we have not defined our network. So we have the nodes 1, 2, I, j, k and n. Okay, so these are the notations given. So I have considered my m node, any node we have to consider. So I have considered the jth node as a old node. One of the old node we have to pick up, because the off diagonal elements impedance is represented between the new node to the existing old nodes. Okay, that's what we have represented as Z1k, 2k, 3k like that. So that is why I have considered m as a j. So accordingly we can modify the equation number 1c as Zkj equal to voltage with respect to the kth node divided by current flowing through the jth node. In the previous case we have considered all the nodes are open circuited. So now for this expression we need the current with respect to the jth node. So we will inject the current again 1 per unit at the jth node. As the same like previous, we will assume all other nodes as a open circuited. So this network we already have. Now we are going to inject the current between the jth node and the reference node of the magnitude 1 per unit. Now let us mark the voltage with respect to the kth node. So that is v suffix k. So from this figure we can write v suffix k is equal to 0. Why? Because we have not injected any current. Here the current with respect to the kth node is 0. So whenever the current becomes 0, obviously your voltage also, because ik into zkk, so you will not get any voltage drop across that. From equation 1c we have equation for zkm. By substituting equation 1d in equation 1c, you will have zkm equal to zmk equal to 0. So because here already the voltage with respect to the kth node is 0, so this becomes 0. Obviously this value becomes 0, and we know the zkm equal to zmk. So therefore all off diagonal elements for type 1 modification, that is whenever you add an element between the new bus to reference bus, all the off diagonal elements will become 0. So this is the expression for the off diagonal quantity. Let us see the complete matrix after type 1 modification. Zbus new equal to Zbus old, which is formed between the 1 to n nodes, and we have a kth node. All the off diagonal elements will be 0, and we have equation for diagonal quantity as Zb. Right? So this is the final matrix after type 1 modification. Now let us see the derivation for type 2 modification. In type 2 modification, we will add an element between the old bus to new bus. So again notations remains the same. Old bus means either you can consider ith node or jth node as a old bus. New bus will be the kth node according to our partial network. So let us consider the network. Now we are going to inject the current I suffix k with a magnitude 1 per unit. Now we are going to write the voltages of all the nodes that are existing in the partial node with respect to the kth. So from the figure we can see V1 equal to Z1k into Ik. So because we have injected the current at the kth node, and this kth node and the first node will have some mutual impedance. Why? Because we have connected the new node to the node which already existing in the network. Okay, this already will have some impedance with respect to the other node. Whenever we connect a new node to the existing network, obviously this will also have some mutual impedance between the other nodes that are existing in the network. So based on that, you can write V1 equal to Z1k into Ik and V2 equal to Z2k into Ik, and we are equating that to the Z1k because we know the magnitude of the current that we have injected at the node k is 1 per unit. So similarly, you can write for the all the old nodes that are existing in the network, and the voltage with respect to the new node is equal to ZKK, which is the self impedance of that network into the current. So let us consider this set of equations as equation number 2a. So now for better understanding, let me consider that section of the nodes separately. That is, we have already the ith node in the partial network and we have taken kth node. This is the new node and this is the old node, and we have added an element which is having the branch impedance as a ZB, and we have injected the current of magnitude 1 at the kth node, and there is already voltage exists between the reference node to the ith bus, which is the Vi, and the voltage with respect to the kth node is V suffix k, and the current flowing through the network, that is in the branch Ik, is Iik. The Iik magnitude, you can see the current is coming in this direction, but the injected current direction is like this. So means both are in the opposite. So now let us write, if you see this portion of the network, Vi acts as a input, Vk acts as a output, and the current, the drop across this element is Iik into Zb. So we know the standard formula that input is equal to output minus the voltage drop. So that is V suffix I is equal to V suffix k minus Iik into Zb. So that is how we have written the equation. Now if you see this network, Iik current direction is this way, but I suffix k current direction is coming like this. Both current directions are just opposite. So you can represent the Iik is minus I suffix Ik, which is the 1 per unit. That is, Iik is minus 1 per unit. So now if you represent Iik minus 1 per unit, now we will get V suffix k is equal to Vi plus Zb. So let us consider this as a 2c. So now let us simplify by using the equations 2a and 2b. So from the equation 2a, we got the relation V suffix I is Zik into I suffix k, which is the Z suffix Ik, and V suffix k as a Zkk into Ik, which is equal to Zkk. So these are the two equations we already got from the set of equations that we have derived. And from equation B, we got a relation V suffix k is V suffix I plus Z into B. So we have in place of V suffix k, we have Zkk. So in place of V suffix k, we have Zkk, and in place of Vi, so Vi is equal to Zik. So we have replaced Vik by Zik, and Zb we are keeping it as it is because that is the branch impedance. So this is the final expression that we got for the diagonal components. Now let us see the derivation for the off-diagonal component. So for off-diagonal component, as usual, elements are linear and bilateral. So we do consider the Zkm equal to Zmk, and for all the nodes that are existing in the partial network, and Zkm equal to V suffix k by I suffix m, and let m be the j. Some old node we have to consider. We have considered the jth node. So accordingly, we can modify. Okay, so these steps are similar like the type 1 modification derivation. Now we are going to inject the current at the jth node, the same magnitude of 1 per unit, and let us consider the rest all nodes are open circuited, and we are going to compute the V suffix k under this condition. So now let us add the current with respect to jth node of the magnitude 1 per unit, and kth node is connected to the ith bus, which is having the branch impedance Zb. So from the figure you can say the V1 equal to Z1j into Ij. So why now the 1j because here I don't have current. So now I can't write the values as a Z1K into IK because my IK current is not there. So now we will write the voltages with respect to the all other old buses to the node where we have injected the current. So V1 equal to Z1J into Ij, which is equal to Z1J again because Ij equal to 1 per unit. And let us write the equation for all other nodes that are existing in the network. So let us consider these equations as a 2C. So this is the one expression we need, that is V suffix K is equal to Zkj into Ij, which is equal to Zkj, and Vi is equal to Zij. Now what is the relation between the voltage with respect to ith bus and voltage with respect to kth bus under this condition? Now if you see, I and J are connected directly parallel. Current is not there. Current is 0 for both the cases. So both are connected using the impedance ZB. So the voltage with respect to the ith bus is V suffix I, and the voltage with respect to the kth bus is V suffix K. So means these are the two parallel nodes that are connected voltages. So since there is no current, so the V suffix K will be equal to the V suffix I. So according to this relation, we can equate these two expressions. So that is Z suffix Kj equal to Z suffix Ij. So from this, we will get to know that we can interchangeably use the K and the ith nodes because both are at the same potential. So according to our convenience, it can be used as a kth or ith. You can interchangeably use this subscript. So now let us mark the final Zbus new matrix after the updation of this off diagonal and the diagonal elements of the type 1 modification. Finally, let us represent the complete matrix after the type 2 modification. Zbus new equal to Zbus old, which is formed between the existing partial network nodes and kth node. We have equation for the off diagonal elements, that is Z1Ik, 2K. These are, so we got the off diagonal elements and Zik plus Zb. So instead of Zik, now I just told you the K and I can be used interchangeably. So now I am going to change my K to I, which is going to be Zii plus Zb. Okay. So this why I change it like this, you will understand better whenever I am solving the numerical. So I hope it is clear. Thank you.